Okay, let's talk about control of mean arterial pressure. Because mean arterial pressure is something that affects the entire body, it has to be controlled by systems which have control over the entire body. There are two of these, the nervous system and the endocrine system. And specifically, in this case, the autonomic nervous system, the one that contains the sympathetic and the parasympathetic. The cardiovascular center, or the part of the brain that's involved in controlling mean arterial pressure, is located in the medulla oblongata, and it consists of three parts: the cardioacceleratory center, which speeds up the heart, and the cardioinhibitory center, which slows down the heart, as well as the vasomotor center, which controls the size of the lumen of the vessels, controls systemic vasoconstriction and vasodilation. Now, we've discussed in the last chapter the cardioacceleratory and cardioinhibitory center and how those increase or decrease heartbeat respectively. Respectively? Respectively. Damn it. Okay, let's talk about control of mean arterial pressure. Because mean arterial pressure is something that affects the entire body, and it has to be controlled by something that has control over the entire body. We have two systems that do this, the nervous system and the endocrine system, and we're going to talk about each of them separately. First, we'll start with the nervous system. Now, the cardiovascular center is housed in the medulla oblongata in the brain, and it includes three different centers or subcenters. Two of them we've already discussed in the last chapter about the heart: the cardioacceleratory center, which speeds up heart rate, and the cardioinhibitory center, which slows heart rate down. We're going to add to this now by looking also at the vasomotor center, which sends signals to the blood vessels to either dilate or constrict. The difference between how the heart is controlled and the vessels are controlled um, has to do with which branches of the autonomic nervous system are used. So in controlling heart rate, we have the sympathetic through the cardioacceleratory center to speed up heart rate, and the parasympathetic through the cardioinhibitory center to slow heart rate down. There is only one vasomotor center, and it only uses the sympathetic nervous system with the hormone or neurotransmitter, rather, norepinephrine. Norepinephrine causes vasoconstriction. In order to change whether a vessel is constricted or dilated, the vasomotor center only secretes more or less norepinephrine. So it only has use of the sympathetic nervous system, and the size of the vessels is controlled by how much sympathetic signal the vessels receive. Now, what I'm going to do in the next few slides is look at the inputs that go to the medulla oblongata, to the cardiovascular center. What kinds of things this center responds to, and then we'll look at the outputs, which is how it responds or what signal it sends to the vessels. Let's take a look first at the general inputs to the cardiovascular center. The things that primarily influence the cardiovascular center are the pressure, which is measured by baroreceptors. Baroreceptors are pressure receptors, and they are mostly located in the carotid and the aortic arteries. The more a vessel stretches, the more those receptors send signals to the cardiovascular center. The less stretched a vessel is, so the lower the pressure is, the fewer signals the baroreceptors send to the cardiovascular center. So we have a direct way to measure pressure. If there's so much blood in the vessels that it stretches, the baroreceptors are screaming, "Hey, pressure is high." If there is not very much pressure in the vessels, then the baroreceptors are sending fewer signals. And the cardiovascular center is able to interpret this and respond appropriately. The other main input to the cardiovascular center is a chemo input, so chemoreceptors. These chemoreceptors measure carbon dioxide and oxygen. They are located in the brain and also in the kidneys. And they sense the concentration of these two gases. Now, how does that tell us anything about pressure? Very indirectly. What this tells us is how much blood is probably going through the lungs. If there is not enough blood going through the lungs, then we would expect that the concentration of carbon dioxide would become high because we're not moving enough blood through for the carbon dioxide to come out of the blood and be breathed out of the body. The concentration of oxygen in the blood also gives us information about the flow through the lungs. If the oxygen concentration is high, then all is good. We've got good perfusion of the lungs. If the concentration of oxygen is low, it indicates that there's not enough blood moving through the lungs in order to pick up the oxygen. Of these two, the concentration of carbon dioxide is far more important because carbon dioxide spontaneously converts to protons, H+, which is acid, and that's also picked up by chemoreceptors. But that influences the pH of our blood, which we'll talk about more when we get to a future chapter that touches on that. Now, all of this information about pressure, which is known as a baroreflex, and the chemistry of the blood, which is known as a chemoreflex, that information comes into the cardiovascular center. The response is to change cardiac output and change vasomotion, or the size of the vessels. Let's take a look at a specific case, break it down one thing at a time. So the first thing we're going to look at is if mean arterial pressure is low, how is the heart going to respond? This should be review. So if pressure is low, the baroreceptors are going to fire more slowly. The chemoreceptors for CO2 should be firing more. The chemoreceptors for oxygen will be firing less. Any of these signals, if they get to the medulla oblongata, are going to cause the cardioacceleratory center to send a signal to the heart with more epinephrine. So this is a sympathetic signal, and it tells the heart to increase heart rate, which increases cardiac output. Increased cardiac output is going to increase our mean arterial pressure. Okay, so that's the response of the acceleratory center part of the cardiovascular center. Now let's look at what happens with the vasomotor center, how it responds. So same situation, pressure is low, so the baroreceptors are firing less, the chemoreceptors for CO2 are firing more, and the chemoreceptors for oxygen are firing less. When those signals reach the cardiovascular center, the vasomotor center responds by secreting norepinephrine, and that causes systemic vasoconstriction. Remember that when all the vessels constrict, that's going to increase mean arterial pressure. Now, if mean arterial pressure is high, then the input from the receptors will be the opposite. The baroreceptors will be firing more, the chemoreceptors for carbon dioxide will be firing less, and the chemoreceptors for oxygen will be firing more. Those signals reach the medulla oblongata, And the cardioinhibitory center sends parasympathetic signals to the heart, which decrease heart rate, decrease cardiac output, and therefore decrease mean arterial pressure. What about the vasomotor center? So, same signals. The medulla oblongata now takes those signals. The vasomotor center secretes less norepinephrine. This is because the vasomotor center only uses sympathetic signals. So it can either send more sympathetic signals to the vessels or less sympathetic signals to the vessels. So now it's going to be secreting less norepinephrine. That's going to cause systemic vasodilation. As the vessels dilate, the mean arterial pressure goes down. Now, there's one special case of input to the cardiovascular center, which the vasomotor responds to. In response to some strong emotional experience, the limbic system, which is what controls our emotions, or not controls them, but it helps to create them and send signals to the body to respond accordingly. Sends input from the vagus nerve to the cardiovascular center. This is why this is called vasovagal. Vaso for vessel, vagal for the vagus nerve. This strong emotional input causes the vasomotor center to almost stop secretion of norepinephrine, which causes a very sudden vasodilation. And allows the blood to pool in the lower parts of the body. When the blood pools in the lower parts of the body, then there's not enough venous return or blood returning to the heart through the veins in order for the heart to have adequate cardiac output. The response is to cause you to pass out or faint, which is what syncope is. So, if you've ever seen someone faint after receiving a strong emotional input, then you've witnessed vasovagal syncope. Now let's talk about end control of mean arterial pressure. There are 5 hormones in the endocrine system which influence mean arterial pressure. The most potent of these is angiotensin II, which is actually part of a system known as the renin-angiotensin-aldosterone system. Aldosterone is the second hormone that we're going to discuss here. It increases mean arterial pressure. In fact, all of these hormones, except for this last one here, increase mean arterial pressure. So why would we have so many ways to increase pressure when we're always hearing about how bad high blood pressure is? The reason is that it takes years and years of high blood pressure to cause the kind of damage that can actually make you ill and possibly kill you. For low blood pressure, it takes minutes. So the body has many more mechanisms for increasing blood pressure instantly, quickly, to keep you from dying of low cardiac output and low pressure. And it doesn't have very many mechanisms to lower pressure because there is no immediate danger there. All right, let's take a look at the first one. In response to low blood pressure, remember there are pressure receptors in the kidney. Actually, I don't think I said that, but there are pressure receptors in the kidney. The kidneys secrete something known as renin, and they secrete it into the bloodstream. Also in the bloodstream is an inactive precursor known as angiotensinogen. This is produced by the liver and is present in the blood all the time. It's just inactive unless it is activated by renin. So when the kidneys secrete renin, renin converts angiotensinogen into angiotensin I. Angiotensin I floats along in the bloodstream, going back to the heart, passes through the heart, and heads into the pulmonary circulation. When it reaches the lungs, the capillaries of the lungs are lined with an enzyme known as angiotensin converting enzyme, or ACE. ACE converts angiotensin 1 into angiotensin 2. This is the active form of the hormone. Angiotensin 2 stays in the circulation, and returns back to the heart, and then is sent out into the systemic circulation, which is serving the body. As it encounters or touches the vessels, the systemic vessels, it causes immediate and very intense vasoconstriction. In addition, angiotensin 2, also as it's passing through the bloodstream, travels through the adrenal glands. The adrenal glands are the ones that sit on top of the kidneys, and it causes the adrenal glands to secrete aldosterone, which is the second hormone on our list. Aldosterone travels to the kidney and causes the kidney to increase fluid retention. It does this by holding on to sodium, and if it holds on to sodium, then water is going to follow the sodium and stay inside the body instead of being released into the urine and lost. Holding the water in the body increases our blood volume. Increased blood volume increases blood pressure. Angiotensin 2 also travels to the pituitary and causes the pituitary to secrete antidiuretic hormone, or ADH. ADH also sends its signal to the kidneys and causes the kidneys to increase fluid retention. We're going to talk about how that works in just a moment. Finally, angiotensin 2, in traveling to the brain, reaches the hypothalamus, and the hypothalamus responds by creating the sensation of thirst, which hopefully will increase fluid intake and therefore blood volume and increase blood pressure. So you can see that angiotensin 2 is an extremely powerful hormone in that it causes immediate systemic vasoconstriction, but also activates other parts of the endocrine system to increase mean arterial pressure. All right, let's take a look at how each of these works. Angiotensin 2, its primary or first response is vasoconstriction, causes vasoconstriction to increase mean arterial pressure. But by activating aldosterone, it increases sodium retention and therefore fluid retention. It also activates antidiuretic hormone. Antidiuretic hormone we're going to talk about more when we get to the urinary system, but it works by allowing more or less water to escape into the urine. And we'll go into much more detail on that when we get to the urinary system. The endocrine system, through the adrenal glands, also secretes epinephrine and norepinephrine, or NE. Norepinephrine, as you recall, is also a neurotransmitter, but both of these, originally known as adrenaline and noradrenaline, are produced by the adrenal glands and released directly into the bloodstream, where they cause systemic vasoconstriction as well, just like the neurotransmitter does. The last of these hormones, atrial natriuretic factor, is produced by cells in the atrium, which kind of makes sense. If there's a place in the body that would be like, hey, the blood pressure is too high and it's annoying me, it would be the heart, because the heart has to work so much harder when the blood pressure is high. Natri refers to sodium. Recall that the abbreviation for sodium is Na. That comes from its original name, natrium. So this is natri. Uretic means urine. So this is the effect of sodium on the urine. Atrial natriuretic factor is sent to the kidneys. The kidneys respond by putting sodium into the urine so that water will follow, and it will increase urine output, which will decrease blood volume and decrease mean arterial pressure.